All right, so we're going to talk about Newton's second law now, more specifically than in the overview. So why don't we start with what we talked about in that overview of Newton's laws. So Newton's second law says that acceleration is directly proportional to the net force and inversely proportional to the mass. And so just as review again, directly proportional means that as the net force goes up, acceleration will also go up. So as this increases, this increases. Inversely proportional means that as one goes up, the other goes down. They're inverses, they're opposites. So as the mass increases, acceleration will decrease. So another way of saying this, the harder you push on an object, the more it accelerates. That makes sense. You push the accelerator on your car more and your car speeds up faster. But on the other side, the heavier an object is, the harder you must push on it in order to cause it to accelerate. It is much easier to push a box full of stuff than it is to push a car. And it's because the mass is greatly different. So the box has a much smaller mass than the car does. And so the smaller mass has a greater acceleration. So what this looks like in an equation form is net force equals mass times acceleration, or F net equals ma. So here you can see that if the force goes up, so if this side increases, then this side of the equation must increase. So this side goes up, this side goes up. That is a direct relationship. Now the other side of this equation is about the mass. So let's say net force is going to remain constant. If mass goes up, then the acceleration is going to go down because it has to counteract each other. Just like whenever this went up, to counteract this side of the equation going up, this side also had to go up. But now that it's happening on the same side of the equation, as this goes up, this has to go down. All right, now in terms of units, force is measured in newtons. So force is in newtons, denoted by capital N. Mass is in kilograms, and if you remember again, Ms. Tolmich's reminder of how you remember that, which is kiss my mass. So kilograms, kiss my mass. And acceleration, just from like everything we've done already, is in meters per second squared. So a way of looking at this equation in terms of the definition. Let's say we've got this guy and he's got a golf club. He is going to hit both of these objects with the exact same net force. Okay, so the F's are constant. He's hitting a small golf ball, which has a very small mass. Well, a teeny mass means it must have a large acceleration. Hence, you hit the golf ball and it flies out into the green. Over here, he's applying the same force to hitting a truck. Now, I would not suggest doing this as a demonstration because whoever owns the truck will probably not like it, but the idea still works. He's hitting with the same force, but now this truck has a much larger mass, so it has a teeny tiny acceleration. So same force, but you can see that inverse relationship between mass and acceleration. So how does this equation explain why two objects of different mass accelerate toward the Earth at the same time? So remember we said that it doesn't matter what the mass is, objects will always fall at negative 9.8 meters per second squared. Well, now we can actually explain why. And the reason why is because the larger mass has a larger force of gravity pulling it down. This will make a little bit more sense whenever we get to universal gravitation. But larger mass has a larger force due to gravity. A smaller mass has a smaller force due to gravity, and these two have the exact same ratio, so F over m and F over m, which equals that 9.8. That's why they fall at the same rate, is because the forces change with the mass. All right, so now let's start with just a few concept type math problems. I know it seems counterintuitive, but We call these factor problems. And so you'll hear me say that a lot. So factor type problems. Suppose you apply the same force to two carts. One has a mass of 4 kilograms and the other has a mass of 8 kilograms. The first question is, which cart will have a greater acceleration? Well, since it's the same force, the only thing that's changing is the mass. And here the mass is increasing. So mass and acceleration have an inverse relationship, which means the smaller the mass, the greater the acceleration. So it's going to be the 4 kilogram cart. Smaller mass, greater acceleration. Now the second part is asking how much greater will the acceleration be? Well, 4 to 8 means that we're doubling the mass. So doubling mass. Because 4 times 2 gives you 8. And so if we look at our equation, F net equals ma, if the mass is doubling, how we do these factor type problems is, you might want to write this down. So step 1 is to mark out any variable that doesn't change. And then step 2 is use a 1, the number 1, as a placeholder if needed. So the idea is we're only looking at what is changing in order to figure out how something else changes. So here we're looking at how the mass changes the acceleration. So we're looking at mass and acceleration. Here it says the same force. So step 1 is to mark out any variable that doesn't change. Well, F net, not changing. Then step 2 is to use a 1 as a placeholder if needed. Well, if we mark out F net, we have nothing on this side anymore. And so we have a change on this side of the equation of 1, which means there is no change. Anything times 1 is itself, so it's constant. And so then we have the mass, which we said doubles. And so we're going to put in how it changes. So mass changes by 2. And we're looking at how acceleration will change. And so then if we solve for that, we'll see that the acceleration will be half. So if you had an initial acceleration of, say, 10 meters per second squared, then if you double the mass, it would be half of the original. So it would be half of 10, which would be 5 meters per second squared. So let's try another example. If the net force remains the same, so force is the same, and the mass triples, what happens to the acceleration? All right, so we go F net equals ma. Always start with the equation. Net force remains the same, so we're going to mark it out. And since we have nothing on this side of the equation, we need to put in a placeholder of a change of 1, which means no change at all, right? 1 times anything is 1. Or 1 times anything is the anything. Mass triples, which means 3 times. So we put in a 3 for the mass, and we try to figure out how the acceleration will change. So we're going to divide by 3, and so the acceleration should be 1/3 of the original. So now, if the mass stays constant and the net force triples, what happens to the acceleration? So F net equals ma. So now the mass is staying constant. So we're going to mark out mass. Now see, we don't need to put a placeholder here because we're just going to mark it out. And what's left is that the change in the force is going to be equal to the change in the acceleration. So if the force triples, we plug in a 3, and we see that the acceleration will also triple. So now these are actually giving us values. If you are given values with units, that's a way to help you out. Factor questions usually have no units. Whereas plug and chug is going to give you numbers with units. Typically. So I push a car with a net force of 40 newtons. If the car's mass is 3,000 kilograms, what is its acceleration? So again, use our equation. F net equals ma. This is our force. Force is in newtons. So 40 equals mass, which is 3,000 times A. And so we're going to divide by 3,000. And so our acceleration will be 0.01333 meters per second squared. So notice in a factor problem, there's no units. It's just saying that the acceleration will be 3 times what the original was. So if the original was 10, again, then it would be 3 times as high, so it would be 30 meters per second squared. So factor problems have no units. No units. But plug and chug problems have to have units. So here we're actually solving for the specific acceleration, so it has a unit of meters per second squared. All right, here's another one. So a net force of 20 newtons upward. If the box has an overall acceleration of 0.23 meters per second squared, what is the mass of the box? So the net force is 20 newtons. The acceleration is 0.23 meters per second squared. And so we're looking for the mass. So we're still going to divide. And so our mass will be 86.96. And remember, the unit for mass is kilograms. Kiss my mass, kilograms. All right, so last example. With what net force must I push on a 1,000 kilogram car in order for it to accelerate at 2 meters per second squared? So again, our equation, F net equals ma. So kilograms is your mass. Meters per second squared is acceleration. And so we're looking for that F net. We have 1,000 times 2. And so our answer would be 2,000 newtons. Force is measured in newtons in the metric system. So this slide is extremely important to understand. There are always a ton of questions on the midterms, on the finals, on tests that talk about what happens if the net force is 0. So the first answer is that the acceleration is 0. So again, if we're using our equation, F net equals ma, if the net force is 0, we can't have an object with a mass of 0. And so if we solve for acceleration, 0 divided by anything gives you an acceleration of 0. So acceleration is 0. Now, what does that mean? If the acceleration is 0, what does it mean? Well, number one, the object could be at rest. You can't accelerate if you're not moving, right? So acceleration of 0 can be that the object's not moving. But there's a second idea. The object is moving with constant velocity. If you're going constant velocity, you have no acceleration, because acceleration is the change in velocity over time. If this is 0, then we have 0 divided by t, and again, we get 0. So constant velocity is also a situation when acceleration is 0. This will become really important when we start talking about start talking about air resistance and objects falling. So acceleration to 0 means an object can be at rest or can be at constant velocity. And just as a reminder, constant velocity means constant speed. So same speed in a straight line, which means no change in direction. So constant speed in a straight line.